now it's time for to get a little hands-on experience with using TEASER for registration and Open3D for visualization of the results in Python. I'm just going to put the QR code here, and then I'm going to switch my computer to another desktop machine, so I can run the algorithms. So if you have Linux, you should be able to follow along. Okay. All right. Looks like I can also keep the can you guys see my screen?
Yeah, we see the zoom in the web browser.
Yeah. So, okay. All right. So let me start with. Let's basically go to our repo. All right. So this is a repo you are probably interested in if you want to work with TEASER. So it's on GitHub. And then you can scroll down all the way to see the installation instructions. So the dependencies are pretty minimum. So you only need eigen3 and to actually run and compile everything. If you want to use a wrapper for FPFH, then you need to have Boost as well as PCL. Of course, you need CMake to generate the configuration files. So I'm just going to open the terminal here and then start from scratch. So let's say you want to clone the repo and play with it tonight, I guess. So let's first go to clone, right? So clone with, we copy the link, and then we go to terminal. And then I'm just gonna make a new folder called, actually, let me make it bigger. Okay, not so sure how to make the fonts bigger.
Any suggestion about how to make the font bigger, guys?
All right, let me actually, hold on. Switch to another
Try
terminal.
Control-Shift++.
Yeah. Hey, thanks. Perfect. All right, so going to make a new folder called TEASER tutorial. And I'm just gonna go to that folder real quick. Nothing inside. So I'm just gonna clone my repo. All right, so let's see what we have here. So this is the repo we're gonna use for TEASER. And then it has everything that we need to run examples. So first thing first, if you wanna make build the repo with CMake, you wanna make another directory. I'm just gonna call it build. And then I'm going to enter the directory and then use the very typical CMake command called CMake. And then dot dot. So that means we want to build it outside, inside the build folder with whatever source we have on the outside. So I'm just gonna do this. And then CMake will do the magic. It will actually download some of the dependencies automatically. from GitHub. So you don't need to do anything. Okay, let's see. And then we have the files ready in the build folder. And I'm just going to call make. Yeah, so it's going to take a while, but it shouldn't take too long. There's not so much to be built. And then after build, if you want to use it in any sort of C++ projects, you want to install it into your library, into your local folder. So let's just do sudo make install. So what it does is basically it moves a bunch of header files to your user.local include folders, and then it moves a bunch of object files to the folder so that other C++ projects can access it. So we have finished installation, and then I'm just going to follow the C++ example shown on the README first, because that's pretty easy. So the C++ example is in the examples folder, and the first example I'm going to show is basically the cpp/pry example. So what it does, if you look at the source code real quick, it essentially creates a pry file into our memory, and then we convert the point clouds to eigen, and then we apply an arbitrary transformation which to the input point cloud. Then we apply the transformation to the point cloud, and then in this example, I added some random outliers and noise. And then, as I've discussed before, create a parameter struct, and then solver with the solver, and then it's going to print out the results. Okay, so to make it, follow the same kind of rule I've described before. So make a build folder, build, and then cmake. And then make. Should be able to build it real quick. And then let's see. And the segmentation fault. Okay, so in this laptop here, in this desktop here, there's one issue that is caused by the underlying PMC library. So basically, for CPUs with threads number more than 12, sometimes it will cause segmentation faults. So one way to solve it, which is also documented in the README file, is to use environment variable defined before the executable to limit the number of threads to 12. So, and then here we have no segmentation faults, and then we have the results printed. So we have here is the expected rotation and estimated rotation. And then the error in degrees is 0.13. And then we have the expected translation compared to estimated translation. And the error in meters is 0.006, very, very small. And then in this case, we have 1,889 correspondences with 1,700 outliers. And then time taken is 0.39 seconds. So so it's pretty fast in this case. And then to make it, I guess, clear on how to actually use it in any sort of CMake project, let's look at the CMake list file. So this is a very minimum CMake list file that you can use to include teaser in any sort of C++ project. So first we have the standard stuff we want to include in a CMake project, and then we basically find package eigen3, and then we find package TEASER PP, and then we add the executable we want to add. So in this case, this is the file we want to add, and then we link it to the TEASER++ libraries. So in this case, we have the core registration library, as well as the IO library, which allows us to import the PLY files. And then this is just for the example, but it copies the PLY file to the build folder so the executable can access the PLY files. Any questions so far?
Jinna, can you go to the script that you ran for the example? Like
Yeah.
where you show all the parameters. I spotted the. Can you scroll down?
Yeah.
Where you define the parameters. Yeah, here. There's a rotation cost threshold. Here, why is it 5e minus 3? It should be.
Yeah, it should be. I think it should be 1e negative 12.
Yeah. Does it matter?
I guess in this case it doesn't matter, but the default is not this value. This is just for the example, I guess.
Okay, yeah. It's worth letting people know that this should the threshold should be much smaller. It should be 1e minus 12, I think.
Okay, so we have Andrew reporting an error in the chat. So it basically says error while loading shared libraries. libpmc.so cannot open shared object file. No such file or directory. So this you need to run ld config after after installing, and you can run ld config and then see whether you can fix it.
Yep, doing so now.
Yeah.
I need to sudo.
Yeah.
Some serious real-time debugging here.
All right, so that ran without any output, and boom, it works. Nice.
Oh, that's nice.
Yeah, so that's that is something I need to add it to README, but essentially it is caused by the fact that making install the shared object files into user/local/lib, but this is not the default Ubuntu linker library search directory, so you need to run ld config to update the directory. But yeah, I'll put that into the README for future reference.
Makes a lot of sense.
So Jingnan, you have a couple of one comment and one question. So
yeah.
One comment is about what Hank was saying about the parameters. In my understanding, the user does not have to change any. So the default parameters are going to be very general. The user does not have to worry about changing those.
Yeah.
The only one that the user may want to change is the noise bound, which is a measure of how much noise one is expecting on the measurements. Is that correct?
Yeah, that's correct.
Okay, so just the noise bound. Okay.
Yeah.
The second thing is about the results that you got. So the example that you are just running took 0.39 seconds.
Yeah. And
how does that, what is the difference with respect to the 20 milliseconds that we got in the slides?
Yeah. So, as mentioned in the paper, I think the scaling of the timing is not linear for our algorithm. So if you have, say, 500 points, it can run like a few 20 milliseconds, but with points higher and higher, especially reaching around 2000 points, it's going to take longer. And one additional factor that can affect the speed is basically the structure of the inliers you have in the data. So in certain cases, it might run faster, especially in cases where there's a lot of outliers. And then in certain cases, it might run slower. But there are some configuration you can change in the parameter files that you can tune to get a better speed, depending on what kind of max click algorithm you use.
And as a user, do I have to worry also the maximum number of threads, which is the parameter that you fixed at the beginning? Like, you know, is it going to have like a huge impact on the performance? Probably, yeah.
I think not like significantly. Like based on my understanding, like if you have say 6 threads versus 12 threads, it's not like a 2 times speed reduction. Yeah, but I think all the performance results I've shown in the presentation are obtained with 12 threads. Yeah.
Okay.
And there are cases where you can run more than 12 threads, but in that case, from my observations, basically the cost of creating threads is gonna overweight the performance gain you get from parallelization.
Got it.
Yeah, so that's the minimum C++ example. And then I'm going to show another example involving Python, which is basically reproducing this GIF here. So we have this using Open3D, which is a Python library. And at least what I think is the best way to use this is using Anaconda or Miniconda, because that provides you a pretty easy way to manage the environments as well as packages. So I'm just going to say create a new Conda environment. Let me actually let me see what it is. And then activate this new environment. Let's see. Oh, yeah, sorry. Didn't change it to Python 3. Yeah, let's just copy this because it remains more straightforward. So what this is going to do is create an environment called teaser _underscore 3D smooth, and it's going to install NumPy. And then I'm going to activate this environment. And then I'm going to install Open3D. Yeah, it's gonna take a while, but it should be pretty smooth given that Anaconda is gonna handle most of the dependencies for you. And we're gonna install as scikit-learn. This is just for finding the nearest neighbor in the feature vectors. Okay, so I believe all the packages should be ready. Yes. So again, go to the build folder. I'm just gonna clear the build folder so that I have a new build with the correct Python interpreter. And then I'm just gonna copy this. So what this says is it's going to use a Python version 3.6 and just make the Python binding. Again, very similar to the C++ example. So so TEASER++ is tested on Ubuntu 18.04. It should run it should also run on Mac. But I haven't seen, again, I don't have a Mac to test it, but if you test it running on Mac and encounter any issues, you post it in the issue board in GitHub. Okay, yeah, maybe not this. So after build, you should have a bunch of folders, and then one of the folders should be named Python. And then in the Python, you should have a Python package ready. And the way to install it is to basically call pip install this. And it should be able to copy all the stuff to the conda environment you have. And we're just going to go to the example folder to run the example. All right. So go back, go to examples, and then this time we're going to do the Python example. So Python 3D Smooth. And then we're just going to run the run the file. So yeah, it's pretty fast, and you can see this is showing the correspondences, right? You should show it clear. Again, a lot of red lines correspond to outliers, only a few green lines. All right, and then zoom out. So after I close this, it's going to show the registered results. Okay, so you can see it's a pretty good registration, right? And then the green dots correspond to the inliers. So like even if it looks like you have a surface, but it's actually just a bunch of points. So the fact that I enlarged the point just to make it look easier on the visualization. And then again, this is a good thing about Open3D. You can change the visualization you want to have any sort of effects you have. Yeah, and again, because I didn't set the environment variable, I have a select fault again. Yeah, so it should have a report on the performance. So rotation error 0.66 degrees, translation error 0.03 meters, and then time 0.034 seconds. So yeah, so this is the same example I showed in the presentation. Yeah.
Gina, quick question. If it is very common to have this issue because of the number of threads, should we put this variable name, like by default, essentially somewhere? Because
I think that's a good idea. Yeah.
Got it. Okay.
Yeah, I think I should be able to detect the number of threads and then change it accordingly automatically. And I think that would be a nice feature to have, actually. I
also have a question again, like from the user standpoint. Let's say I take this example, right? You have this example with 2-point clouds. How easy is to change this example to feed the 2-point clouds that I have? Like how can I run on my point clouds the same example?
So there's an ongoing issue. Sorry, by issue I mean a GitHub issue. Basically, a discussion I have with a user to basically show a very simple tutorial on how to adapt this script specifically to any sort of point clouds. But in this case, it should be pretty simple. So if you just look at the script, so So here we have a bunch of functions just for drawing, so not relevant for just running. Yeah, a lot of visualization functions. If we go to this, so this is a function that basically find mutually closest key points. You can just take this function as it is, and then run on any sort of feature matrices you have. And then this basically uses the KD tree algorithm to find the nearest points. And then this function basically takes the output from the nearest matching function and then execute a global registration on it.
So, but just to be clear, I do not have
Yeah.
to worry about any of these as long as I create source and destination matrices in the right way. I do not have to worry about this, right?
No, you don't have to worry about this.
Okay.
Yeah. And then you can, I think this script, like you can just copy and paste a lot of stuff from it if you want to adapt it to your own point cloud. Yeah. I think the difficult part would be figuring out what is the best feature extraction algorithm you want to use for your point cloud.
Which will be outside, like it will be even before, of course, calling teaser.
Yeah, it will be before calling teaser.
Do we have some function? I know that you mentioned PCL for FPFH for this type of feature called FPFH. Is it something that is somehow included somewhere in the repository, or is completely external to it?
So Open3D provides a bunch of different features. You can use a PFH algorithm from Open3D to get a PFH in Python. And then the 3D SmoothNet feature extraction algorithm I mentioned in the presentation also has, well, it is written in Python, so you can use it in Python directly. And a lot of learned feature extraction algorithms are implemented with a Python interface, so you can use those pretty easily. Yeah.
Cool, thanks.
Great. So yeah, so that should be it. Any more questions?
This is not a question so much as a comment, but you were talking about 99% outlier rates. So it sounds like even if you pick a feature detector that's just okay, even if you've only got like 1 to 5% of the feature points actually matching up, it'll still be fine. Is that?
Yeah. So that is theoretically the case. A lot of time with handcrafted feature descriptors like FPFH, the rate might be lower than 1% inlier rate, and a lot of case it will have actually very confusing correspondences that completely doesn't make sense. So yeah, so we don't recommend using handcrafted feature descriptors just because it is like actually pretty bad in real applications. For learned feature descriptors, I believe they will have better performance depending on the training data set you have.
Good to know. Thanks.
No problem.
I have one final question. I don't know if there are other questions here, but I have a final question about MATLAB, right? So you cover C++, you cover Python, and you mentioned that you have MATLAB support. For the MATLAB side of things, to have it up and running, it's just a matter of following the same tutorial which is on the README, or there is something fancy to do there?
Yeah, there's a tutorial in README, and you should be able to just run it.
Okay.
Yeah.
Okay, guys, unless there are other questions, I want to thank Jingnan for putting this together. It's like, the real-time debugging was pretty exciting, was very cool actually. And the presentation was very clear. Thanks for taking the time, Jingnan, to prepare these and to give us this tutorial. And that's pretty much it. Thank you.
No problem. Thank you.